Yes, Nikhil Srivastava from Microsoft Research India. He'll talk about spectral sparsification.
Oh, thanks, Ravi. Can everyone hear me? Yeah. Okay. So this is about succinct representations of graphs, the basic object is it's an undirected graph. So it's an undirected graph on n vertices, and we're going to look at weighted graphs. So they have some non-negative weights, and as you know, graphs can be used to represent all kinds of data. So I'm not going to say what that is, but the basic goal is to find a sparse approximation of a graph which preserves some of its interesting properties that we're interested in. So, what we would like to happen in graph sparsification is shown in this picture. You're given a graph G on n vertices. It's an arbitrary graph. It could be dense. It could have up to n squared edges. And you would like to find a sparse graph H on the same set of vertices, so the same n vertices, but sparse, which means that it should have, like, say, order n or order n log n or something like that, edges. I'm going to allow the edges in H to have different weights from the edges in G. My only constraint is that there shouldn't be too many of them. And I want H to approximate G in some natural, well-defined sense, which is useful for some applications. And there are a couple of reasons for wanting to do this. So the main practical reason is that it's like a form of compression. H is, it takes much less storage. It's much faster to run computations on. And then there's also sort of a mathematical reason that if you can show that you can do this for all graphs or even for, say, the complete graph, it's an interesting statement. Like if you do this for the complete graph, you can get an expander graph. Okay. So, the intended application is, as Andrew told you about this morning, it's something like this. You're given some big graph. So I got this picture from Nick Harvey, and you want to run some algorithm on it, but it's going to take a lot of time. So instead, if you have a fast sparsification algorithm which preserves whatever essential property you're interested in, you run that first. It doesn't take too long, and you get something maybe much smaller, and then you run the algorithm on that, and you get some approximate output. So whether or not you can do this, of course, depends on what property you want to approximate. So what you mean by approximation. And one of the first sort of strong notions of approximation for which this was shown to be possible is cut approximation. So this was introduced by Benczur-Karger in 1996, and Andrew talked about it this morning. He already defined it, but I'll define it again. So this is relevant if you're interested in the combinatorial structure of a graph. So we say that a graph H approximates a graph G if for every cut, so that's for every subset S of the vertices of G, which is the same as the vertices of H. So if for every cut S, the total weight of edges leaving S is approximately the same in H and in G. Okay? So what you would like to happen is shown in this picture here. On the left, you have some cut in G. It has a whole bunch of edges crossing it. On the right, you have the same cut in H. And H is sparse, so probably there are fewer edges crossing it. But the point is you've adjusted the weights in a way that the total weight is about the same for this cut, and you want it to be the same for all cuts, all exponentially made cuts. Okay. So is this ever possible? Okay, so here's one example where it's possible. So if the input graph is a complete graph on n vertices, then this is possible. So you take G, it has n squared, order n squared edges. It's a dense graph. And then it turns out that a very good sparse approximation for this graph as far as cuts are concerned is to take a random d-regular graph where d is a constant like 3. Okay? So take H to be a random d-regular graph. This graph is, has degree d. It's very sparse. It has constant degree. But now let's look at a cut. So let's just fix a cut S. So the weights of cuts in the complete graph are, they're sort of trivial. It's just the product of the sizes of the two sides. If you look at the same cut in H, it's a random graph. The expectation is about what it should be scaled by d over n. Okay, so the density of edges, the degree, this has d over n fraction of the edges of the complete graph. So you expect the number of edges crossing the cut to be d over n times the product of the sides, right? But now the amazing thing is that actually you can show that this holds with high probability for all the cuts simultaneously. Okay? So this sparse graph somehow has the same cut structure as the complete graph scaled by the appropriate constant. Okay. And then of course we want the cuts, we want them to be 1 plus epsilon close, let's say. So then you just blow up all the weights in the expander graph by n over d, and then you get that the ratios of the weights of all cuts are about 1. Okay. So So Benczur and Karger proved this like amazing theorem that you can do this for all graphs. So given any weighted graph, you can randomly sample the edges according to some carefully chosen probabilities, which depend on the connectivities, which Andrew talked about earlier. And you can get, so you can't quite do as well as the expander graph, but you can get n log n over epsilon squared edges, and you can approximate all cuts up to 1 plus minus epsilon, and you can do this in nearly linear time. So if you're interested in anything like min cut or max cut or anything like that, then you might as well just do this first, because as far as cuts are concerned, G and H are the same, and this is much smaller. Okay, so what I'm going to talk about today is this different, stronger notional approximation called spectral approximation. And you can think of it as being motivated by physical processes. I often think of it as like a physical approximation. So anyway, the central object in this notion of spectral approximation is Laplacian matrix. So it's a matrix associated with a graph, like the adjacency matrix. And for a graph on n nodes, it's an n by n symmetric matrix whose rows and columns are indexed by the vertices. It's given by D minus A, where D is the matrix containing the degrees, and A is the adjacency matrix. But the more enlightening way to view it in this context is this next expression. It's a sum of outer products over the edges of the graph. So if the graph G has edges E with weights Wij, then the Laplacian of the graph is just the sum of Laplacians of the edges. And a Laplacian of an edge is a very simple matrix. It has 4 entries. It has ones on the diagonal and minus ones on the off diagonal. Okay? So a Laplacian is the sum of these outer products, which are rank 1 matrices, and each one corresponds to an A. Okay. And the thing we're most interested in about the Laplacian here is the quadratic form. So if I have a function on the vertices of the graph, if I have a vector in Rn, the quadratic form x transpose Lx, it's easy to see, is just the sum of differences squared, sum of xi minus xj squared over edges ij in the graph. And this is sort of the natural notion of energy on the graph, and it comes up in a bunch of different settings. And from this identity, a couple of things are sort of immediately clear. So the first is that it's a Laplacian is positive semi-definite matrix. So this quadratic form is always non-negative, so all diagonals are non-negative. And the other thing is that for a connected graph, the kernel of the Laplacian is exactly equal to the span of the constant vector. Okay? So I'm saying that because I'm going to talk about L inverse in a lot of places, and that's it's not invertible. But all Laplacians have the same null space. All connected Laplacians have the same null space, all one vector. So I'm just going to ignore that and talk about L inverse in a bunch of different places. Okay. Okay. So as I said, it's like a natural notion of energy on a graph. So here's an example of what the Laplacian quadratic form looks like. So I have a graph here. And I have some potential on the vertices, so that's just a vector in Rn. It assigns numbers to every node. And the Laplacian quadratic form, I just look at the differences squared over the edges and add them. Okay? And now the point is that the reason I said this is a physical notion is if I were to view the graph as an electrical circuit in which each edge was a 1 ohm resistor, and I took these numbers to be electric potentials, then this sum of squares is actually the energy dissipation of the electrical flow. Okay? Similarly, if I viewed the edges as springs, it's the energy stored in the spring. Okay, so this encodes some sort of physical properties of the graph. I can look at a very different kind of test vector. If I look at a 0, 1 test vector, so I just put 1s on some subset of the nodes and 0s elsewhere, it turns out I only get 1s for the edges that leave the set of 1s. So if I evaluate the quadratic form at 0, 1 vectors, I get cuts. So for any cut S, if I look at x transpose Lx for x, the characteristic vector of the cut, I just get the total weight of edges leaving the cut. So it's just a sort of very simple calculation. So in addition to encoding these energy properties, it also, as a subcase, encodes the entire cut structure, which is the combinatorial property. Okay. So in the language of the Laplacian, what Benczur and Karger showed is that for every graph G, there's an H, so the Laplacian quadratic form is preserved after 1 plus minus epsilon factor on 0, 1 vectors, 0, 1 test vectors X. Okay? Okay, and the stronger notion of approximation introduced by Spielman and Teng in 2004 is, I'm going to say that H approximates C if this holds for all vectors, not just 0, 1 vectors. Okay? So I actually want to maintain multiplicatively this energy functional for all potentials. Okay. And you want to think of this as just saying two graphs are electrically equivalent. Okay? So as electrical circuits, the energy dissipation is the same. And they proved, oh yeah, and from now on, I don't want to keep writing X transpose Lx all over the place. So I'm going to use this positive singular finite matrix notation. So A less than B in this less than just means the quadratic form of A is pointwise less than the quadratic form of B. Okay, so I guess everybody's okay with this. Okay. And yeah, and what they proved is they proved that this also always exists. So for every G in nearly linear time, we can find a graph H with n log to the 8th n edges over epsilon squared, and it is a spectral approximation, which is strictly strong. Okay, so why would you be interested in doing this in the first place? There are a bunch of reasons. The actual reason why they studied this, and the most compelling reason, is that this notion of approximation is very useful in solving linear equations in Laplacians. Okay, so solving linear equations in Laplacians is very useful in physics. So it's if you want to solve an electrical flow problem, it's a linear equation in Laplacian. And it's useful in solving other differential equations, and it's used a lot in, I mean, it occurs very naturally in science. So the point is, if you want to solve Laplacian equations fast, using an iterative method like conjugate gradient, if you want to precondition the Laplacian, what you need is actually exactly this. You need a spectral approximation of the graph. Okay? If you want to precondition one Laplacian by another, it corresponds exactly to finding this notion of spectral approximation. This is what motivated Spielmann and Teng. And they were interested in getting really fast algorithms for solving Laplacians. So if you have a graph on m edges, then the fastest thing you can do is look at all the edges, which is order m time. The naive thing to do if you want to solve Lx equals b is n cubed Gaussian elimination, and there are a bunch of other direct methods, but all of them are worse than n squared. And what Spielmann and Teng did is they used this and a bunch of other things. They came up with all these things to come up with an algorithm that does it in m nearly linear time, m polylog n. And then after several refinements, this has been reduced to m log n. So you can now solve Laplacian linear equations as fast as sorting, basically. Okay, so this is the main motivation. The second motivation is it's just from a mathematical point of view. If you preserve all the eigenvalues, you preserve additional properties that are not directly preserved by just preserving the cuts. Like you can say things about random walk structure, mixing time, and things like that at a finer level of detail. And sort of the third reason in retrospect is that even though spectral approximation is a stronger condition than cut approximation, it's actually mathematically much more tractable in some ways. So it's almost easier to prove these results than proving the cut results. And you could prove stronger results. Okay, so let me show you some examples of, again, what spectral approximations look like. So, here again you have the complete graph, and you take a random irregular graph. I showed you that all the cuts are preserved up to 1 plus minus epsilon. Actually, the whole quadratic form is preserved. You can prove this. And so again, a random graph is the right approximation for the complete graph. And the dependence here again is if you want 1 plus epsilon approximation, you need degree about 1 over epsilon squared. Here's a slightly more complicated example. It's a dumbbell graph. You have two complete graphs joined by a single edge. And the right approximation for this is to approximate each of the complete graphs by a random irregular graph and just approximate the edge by itself. Okay? And this works out because this sparsification, this type of approximation is a linear property. So sum of sparsifiers is the sparsifier of the sums. So you just break up the graph into pieces you can handle and then just add them. Okay? And this example shows several interesting things about this problem. Namely, the edge in the middle is the most important edge in some sense. You can't delete it. If you delete it, you disconnect the graph and you don't have any approximation. On the other hand, it also has the lowest weight, and that weight is order n factor less than the weights of the edges in the complete graph parts. Okay, and that's somehow because those edges are compensating for the other edges that were deleted. So this example actually shows that even given an unweighted graph, you often need to have a weighted graph with widely varying weights in order to get a spectral approximation. Okay, so what I'm going to show you is how to do this for every graph fast, and the proof is essentially going to have like two parts. So in the first part, I'm going to reduce this problem about approximating graph to a purely linear algebraic problem, which has nothing to do with graphs. I mean, of which graphs are a very special case. Okay, and then I'm going to show you how this linear algebra problem is solved essentially just immediately by these matrix Chernoff bounds, which Joel talked about a couple of weeks ago. And then I'm going to show you how to do it quickly, and in the end I'm going to show you I'm going to talk about a result of Kellner and Levin, which shows you how to do it in one pass in a streaming algorithm, but not dynamic as Andrew talked about, just a semi-streaming model. Okay, so reduction to linear algebra. So remember that this is what we wanted to do. You're given a graph G, you want to find a sparse graph H, so that the Laplacian matrix of H is sandwiched between G and some constant times G, which I'm going to call kappa. Okay? And you want H to be sparse, right? Okay. So assume for the rest of the talk G is unweighted. Everything works when it's weighted. Assume it's unweighted. And I'm going to rely on the fact that the Laplacian it has a special structure. It's written as a sum of outer products over the edges, right? That's just the definition I showed you earlier. And I don't want to keep writing delta I minus delta j, so I'm just going to, so delta I is just a vector with 1 in position I. I don't want to keep writing, I'm just going to write b sub e for the signed incidence vector of an edge e. So it has a +1 in one of the nodes and a -1 in the other nodes. It doesn't matter which. Okay? So Laplacian is the sum of outer products of incidence vectors over the edges of the graph. Okay. So now I want to find a sparse graph H that approximates G. I'm going to restrict my attention to weighted subgraphs of G. Okay? A weighted subgraph of G is a graph which doesn't have any edges that are not in G, but the weights of the edges that it does have can be anything, can be different. Okay? So if I have a weighted subgraph H of G, then actually its Laplacian is a weighted sum in the same outer product. Okay? If it has weights S sub E, it's sum of SEBEB transpose. The point is it only uses the same outer product. Okay? This is sort of a trivial fact that I'm saying here. Okay, so now given G, find sparse H, so the Laplacians are close. I know that Laplacians are sums of outer products, and H is a weighted sum of outer products. So this is just saying, given a sum of outer products of incidence vectors, which is my graph G, find sparse scalars. So find a sparse reweighting. Okay, these are the S sub B that define H, such that this reweighted sum approximates the original sum. Okay, so I'm just changing notation. I haven't done anything. I'm just saying that finding weights for these outer products is the same thing as selecting edges and selecting weights from the edges. So this is the graph sparsification problem. Now I'm going to do something that seems ridiculous. So I know a lot about these vectors. They're these signed incidence vectors of edges. I'm going to observe that this is a special case of this much more general problem. Given any sum of outer products, which may have nothing to do with anything, find a sparse set of weights S sub E, so that the weighted sum approximates the original sum of this kappa factor. Okay? So I just threw away everything I knew about combinatorics or the fact that it came from a graph. Okay. This is a purely linear algebra problem. And now I'm going to observe something also very general, but actually very powerful, which is this problem is equivalent to solving this problem, which is a special case in which the sum of the outer product is equal to the identity. Okay? So previously I had capital V equal to any sum V transpose. One special case is when they're equal to the identity. And the proof of why this is equivalent is also sort of very simple. Basically, if I'm given a bunch of vectors that don't add up to the identity, say they add up to some capital V, I look at the rescaled vectors, capital V to the -12 times V sub E. Okay, so I have some vectors, they define some ellipsoid, the quadratic form defines an ellipsoid. It's not the sphere. I just apply an affine transformation to turn it into the sphere. Okay? Now I look at these V primes, which are the rescaled vectors. They are, by construction, they add up to the identity. Okay? So sum of V prime transpose is equal to the identity. Just sort of by construction. But now the point is, if I find a sparse approximation of V prime, the same weights will also work for V. And the reason is that this positive semi-definite ordering is preserved under multiplication by invertible matrices. Okay? So if A less than B, I can multiply by M on both sides. Here, basically, if I approximate the identity and then I multiply by V half on both sides, I approximate V. So I'm just saying, it's a generalization of the fact that if you want a multiplicative approximation of a number, you can scale everything by a constant and change anything. Okay? Okay. So this is the core problem that I want to solve. Given a decomposition of the identity, find a sparse set of scalars not negative, such that this reweighting also approximates the identity. Okay, and geometrically what this problem looks like is you're in Rn, you're given m vectors, some v sub e, and they add up to the identity. And what that means is that the second moment in every direction is equal to 1. So if I look at any unit vector u and I look at sum of u inner product v squared, I just get 1. I'm just trivially writing this down in different language. And what I want is I want to find these weights s sub e, most of which are 0, so they're sparse, right? M could be anything, but I want to find at most roughly order n of them non-zero, which stretch these vectors around in some way. So these are these orange stretchings of the same vectors. And now I want this thing to be close to the identity, which just means I want all of its eigenvalues to be between 1 and kappa, which just means that if I look at the second moment ellipsoid of this thing, I want its principal axes to have length between 1 and kappa. Okay? So I want to preserve the shape of the sphere. This is a sort of, it's just a linear algebra problem. Okay? So are there any questions about the statement of this problem? Okay. Okay, so this, so I did that because I'm now going to apply some very general tools to solve this problem. But actually, this reduction gives you a very sort of tangible intuition about what's going on in this graph sparsification problem. Okay, so let's just look at what it does to some actual graph. Okay, so consider one example where the input graph is G. Now write down its Laplacian. It's the sum of the outer product of its incidence vectors. That actually turns out to already be I'm isotropic. Isotropic just means that the sum of outer products is the identity. That already turns out to look like the identity. All the eigenvalues are the same. So then when I rescale it by Lg to the minus half, in order to make it a sphere, nothing happens. I just get the same thing. Okay, fine. But now look at this graph. Something very interesting happens in this graph. I take the dumbbell graph. So it's two cliques joined by a single edge. If I look at its Laplacian, it's a sum of outer products of some incidence vectors, which sort of look like this. They have two bunches corresponding to the cliques, and then they have one vector that's orthogonal to all the other vectors, just sticking out. Okay? And if I look at the second moment ellipsoid of this thing, right, it's really squashed. Okay? So it's really big in a bunch of directions, it's really squashed in one direction. And the direction in which it's squashed corresponds to the one edge you can't cut. Okay? So the squashed directions correspond to small cuts. And now when I rescale it by the inverse of the Laplacian and turn it into the sphere, this one vector gets stretched a lot. Okay? So what this is doing is it's sort of identifying what the important vectors are for me, this rescaling. Okay? And the reason it makes a lot of sense is because I'm interested in a multiplicative approximation of the quadratic form. So all directions are equally important. Right? And if I have something that's really squashed, I might not see it. It might just show up as noise compared to the rest of the directions. When I do this rescaling, it reveals the vectors that are critical, like this bridge edge. Okay? So that's sort of the intuition. Okay, there's something even nicer, which is, let's just look at what the vectors are for a graph, right? So for a graph, you start off with these incidence vectors BE, which I have a +1 and a -1. Then I'm interested in reducing it to this approximating the identity problem. So I rescale them by Lg to the -half, where Lg is the Laplacian. And now what are the norms of these VEs, of these rescaled vectors, right? So it's a norm of Lg to the -half BE squared. The norm squared is just the inner product. So I open the norm squared. I get that this is a quadratic form in the inverse of the Laplacian. Okay? And I told you earlier, and it's easy to check with Ohm's law and Kirchhoff's law and things like that solving Laplacian linear equations is the same thing as electrical flow. So these numbers are actually equal to the effective resistances of the edges. So the length of the vector corresponding to E is equal to the effective resistance of that edge in the graph T. And effective resistance is again this electrical picture. You have a graph. It's the potential difference induced across the endpoints of an edge when you put a unit current through it. Okay. So this is sort of very intuitively very satisfying to me anyway, which is that you're interested in getting an electrical approximation of a graph, and the notion of importance of an edge is also a strictly electrical notion. It's effective resistance. And yeah, and so this is the intuition I just said about it, that higher effective resistance means more important, and this rescaling exactly sort of reveals this. Anyway, so that's the sort of graph intuition. Now let me just show you how to solve this very general problem. Given a decomposition of the identity, find a sparse reweighting which is close to the identity. And I'm going to solve this in a randomized way. And as I said earlier, it implies the graph sparsification problem. And so I'm just going to call the vectors v sub I, because it's in more generality than this graph. And here I'm just going to use a matrix Chernoff bound. So I'm just going to do random sampling. Okay? So I have a bunch of vectors. I have m. I have lots of vectors, maybe much more than n log n, right? I want n log n vectors which are close to the identity. I know that the average of these vectors is I know the sum of these vectors is the identity, right? So I know that on average, if I pick a random one, it looks like the identity. So, just like there are concentration inequalities for sums of independent random numbers, there are these concentration inequalities for sums of independent random matrices. And this is one of the first really strong ones is due to Rudelson. And it's exactly this statement. If you have a decomposition of the identity, if you sample the vectors according to their length squared, if you take n log n over epsilon squared samples, and of course you rescale them by 1 over the probability just to make it an unbiased estimator. If you do that, then you get within 1 plus minus epsilon of the identity. So, at this point, there are more modern tools. There's like Alsweed Winter, and there are results of Prop, and there are results of lots of other people that you can get slightly finer bounds than what Rudelson did, but this is sufficient for this case. Okay, so this gives you an algorithm for sparsifying graphs. It just says, for a graph, compute the effective distances, take n log, yes? Oh yeah, I'm sorry, there are i's missing on the bottom. Yeah. So yeah, this is saying all the eigenvalues are between 1 plus minus. Yeah. Okay, so yeah, the algorithm will just compute the effective resistances and take n log n over epsilon squared samples and that does it. Okay. So that's an algorithm. It's not a fast algorithm because how am I going to compute the effective resistances, right? So this is something we did in a paper with Dan Spielman. So here's what you do. You again observe that this Laplacian is the sum of outer products, and then I'm going to just define a matrix which has all of these incidence vectors as its rows. This is a signed edge vertex incidence matrix. It's a transpose of the matrix that Andrew talked about this morning. And then the Laplacian is just equal to B transpose B. Okay, so that's also an easy to check fact. And now the main observation is that these sampling probabilities, these effective distances, are actually pairwise distances between a certain embedding of the vertices of the graph. Pairwise distances squared. Okay? So these norm of VE squared is this quadratic form in LG of the LG inverse. Okay? But now I know B transpose B is equal to LG, so I just throw an extra one in there. You can think of B as the square root of L. Okay? And then, I do some manipulation. Like I get this very sort of nice identity that the effective resistance of an edge is the distance between its endpoints squared in this embedding given by the incidence matrix times the inverse of the Laplacian. This is an m-dimensional embedding because the incidence matrix is m by n. Okay. So this is the main fact that we're going to use. That the effective resistance is a squared Euclidean distance, and we want these numbers quickly, right? So if we want, there's some distances between vectors in m-dimensional space. We want them quickly. We don't want to solve m linear equations or something like that. So then the point is we only care about distances, and when you only care about Euclidean distances, you should do Johnson-Lindner-Strauss, right? So I only care about distances between these vectors BL inverse delta I, columns of BL inverse, right? So I'm just going to apply a random projection Q of dimension basically log n, and I project all these into some low-dimensional space. I look at the distances between columns of Q BL inverse, and these are approximately what they should be by Johnson-Lindner-Strauss. Okay? And now the point is I can compute. So I do this, and so the point is I never explicitly compute BL inverse. I just compute Q BL inverse. Q BL inverse is a log n by n matrix. It's very small. And the point is I can compute Q BL inverse by solving Laplacian linear equations, right? So the rows of Q BL inverse are solutions to random electrical flow problems, is what they are. And at this point, there are nearly linear time algorithms for solving these equations. Okay? So computing each row of Z takes some nearly linear time. There are log n of them. So I can do everything approximately. And a key point in all of this is that computing the effective resistances very crudely up to any constant error is enough. Okay? You don't need to get close. Even if you want 1 plus epsilon quality sparsifier, you can compute the resistance up to a factor of 100 and just take 100 times with any samples. That's fine. Okay, so this is the algorithm, right? It has two parts. You're given a graph. In the first step, you compute this random projection of this embedding by solving log n Laplacian systems. And now I showed you that these numbers are equal to the effective resistances. In the second step, you just take 9 n log n over epsilon squared samples with respect to these numbers, and that's it. And then there are several improvements of this due to Kudus, Levin, and Peng, who have reduced the running time. So I think this gives you m log to the fifth or something, and now you can get m plus n log to the fourth or something. I mean, you can get improvements on this running time by doing basically much better analysis of this than we did. Okay. So I also want to say that there's a connection to low rank approximation here, which has been mentioned many times in this workshop by Petros and Mike and others. So the point is actually these numbers, these norms, these effective distances squared, they're actually the leverage scores of the incidence matrix, if you know what leverage scores are. Okay. So actually this sampling algorithm is identical to this length squared sampling algorithm of Friis-Karan-Mampala and Rudolph-Rashinin. Except now we want a low rank n approximation of the matrix. Okay, so it's not actually low rank. And there are two important differences. So one is that this rescaling things to become the identity, it gives you a multiplicative approximation instead of an additive approximation. This is what you cannot do in general, because in general you need to do matrix inversion to do this, right? And you can do it here because you can invert Laplacian matrices quickly. And then the reason you can compute these leverage scores quickly, which also you cannot do very quickly in general, is because, again, because of Laplacian solvers, because it comes from graphs. So the fact that this works has nothing to do with the graph. The fact that it can be done quickly is exploiting the properties of graphs quite heavily. Okay. Okay, so I just want to mention that actually, if you don't care about running time, you can even remove this log n factor. So there's a deterministic algorithm due to Batson, Spielman, and myself, which gets 4n over epsilon squared. But it's mn to the cube, mn cubed or something like that. So I mean, okay, special case of this is the Laplacian, but a good, one question is, can you do it in any kind of reasonable, running time? How much time do I have? Okay, so now I'm going to present a result of Kellner and Levin from 2011, which shows you how to do this in one pass in a streaming algorithm, but in the semi-streaming setting, which is strictly weaker than the dynamic setting which Andrew talked about this morning. So here, suppose you're given like a really big graph which you can't even store in memory, and you're like, you don't want to just load it into RAM and run the algorithm that I told you about. You're slowly getting the edges in some order. So it's a semi-streaming setting. So you're getting edges that are being added to the graph. You're not getting any deletions, like what Andrew talked about. Okay. So you're getting a sequence of edges, and what you would like to do is maintain a spectral sparsifier of the edges you have seen so far in memory, and this should have size n log n, or n log n or epsilon squared. It should have small size. Okay. And you would like to maintain this as the edges are coming in, with small update time, preferably. So this is what's happening. You keep seeing, you keep getting these edges, and you want to update your sparsifier h as you see more and more edges, and this thing keeps changing. And the constraint is, of course, h cannot contain too many edges, so you can't just keep adding everything. You have to delete edges once in a while, and you have to do this in some way which preserves the property that this is a spectral sparsifier of G. Okay. So there's a naive sort of way to do this, or to try to do this, which is, okay, you keep seeing edges, just keep adding them to h until h gets too big. So suppose you have some threshold like, I don't know, 10n log n. When h gets to like 20n log n, you have to do something, right? You have to make h smaller. Okay, so okay, you constructed h. Now you wait until it becomes too big. You wait until it becomes like twice as big as you want. And call these new edges that you need to do something with gamma, okay? So you have h, which is a spectral sparsifier of G, and you have gamma. And you would like to find the spectral sparsifier of G plus gamma, right, which is updated gamma. Well, you could just look at h plus gamma, right? That's just adding the edges that you saw. But this is not sparse. This has twice as many edges as it should have. It is a 1 plus epsilon approximation of G plus gamma, because this notion of approximation is linear. Okay? If you want to reduce its edges, you could just sparsify it again, right? You could sparsify this and get a 1 plus epsilon approximation of that, which is 1 plus epsilon squared approximation of G plus gamma, right? But then, of course, this doesn't work, because if you keep doing this, your error builds up very quickly, and you can barely do it for any number of steps. Okay, so this doesn't work. Okay, so here's the problem we're faced with, right? You're given a sparsifier of a graph G, and you're given some new edges gamma that you have to take care of somehow. And you want to construct h prime, which is a sparsifier of G plus gamma, essentially just given H. So this is what we were not able to do, right? So the main idea that they have in this paper is that you should strengthen your induction hypothesis. You should notice that you actually have more than just a sparsifier of G. You actually have a sample from the effective resistance distribution of G. Okay? So earlier we proved that if you take a graph and take n log n samples from its effective resistance distribution, you get a sparsifier. So let's assume that you actually have that, right? So this is a strictly stronger thing. And now the goal is, given such a sample, can you construct a sample from the effective resistance distribution of G plus gamma, which will, of course, be a sparsifier of G plus gamma? Okay. Okay. So how would you do this? So let me show you a much simpler sort of toy problem, which is what, I don't know, I thought of when I tried to understand what was going on here. So suppose you're given a stream of positive numbers, xi, okay? And at any time, you want to maintain a random sample from the distribution which picks an index I proportional to xi, okay? All the xi seen so far. So that's a distribution p sub t, which is just xi divided by the sum of the xi you saw so far. Well, so, I mean, there's a very sort of clear way to do this. So suppose at time t, you have a sample from pt, right? Capital X, right? There's a way to use it to generate a sample from pt plus 1, right? So you, I mean, I think it's called rejection sampling, but I mean, basically what you do is very simple. It's in this box. So you receive this new number x sub t plus 1. This updates your probability distribution, right? And basically you keep x, the sample you had before, with probability, whatever its probability is now divided by whatever its probability was before. And otherwise, you just add the new element that you added. So, I mean, this is sort of, I mean, you can view this as, okay, I mean, the proof of why this works is sort of just, you can view it as conditioning on picking something from the first t or the last one or something like that, okay? So, I mean, are people clear on why this works? I mean, it's sort of just a pretty easy thing. Okay, so this is a way to use a random sample from some distribution to generate a random sample from some updated distribution. But I'm using that the numbers here are positive, okay? So I'm crucially using that the numbers are positive. If the numbers are negative, this doesn't work, right? If the numbers are negative, then I could have the probability for an element could increase as time goes by. And then if I've already thrown it away, I'm out of luck, right? So, so if you have a bunch of positive numbers, you can do it. So basically, I'm going to try to do the same thing for my resistance sampling. Okay? So I'm going to rely on two facts about effective resistances to achieve this. Okay? There are two facts. So the first, or two facts about the sampling process. So the first fact is that the sampling probabilities are effective resistances, right? Okay. So I'm given a sample H, which is a sample from the resistance distribution of G. The second fact is that sparsifying a graph preserves effective resistances. So this notion of spectral approximation that I told you about preserves the Laplacian quadratic form, which preserves effective resistances are this electrical property that's a function of the Laplacian quadratic form. So it also preserves effective resistances. So this means I can actually, even though I don't have G with me right now, I can read off, I can figure out the effective resistances of edges in G, but just by looking at the effective resistance of the corresponding pair in H. Okay? And the third thing is that resistances are monotone decreasing as you add edges to a graph. Okay? So if I mean, this is physically very clear. If I take a circuit and add some wires, the resistances are only going to go down. Okay? Okay, so these are the two properties, and here's the proof of the two properties. It's very simple. The resistance is, as I told you, a quadratic form in the inverse of the Laplacian matrix. And the fact that I'm using is that if G is less than H in this positive semi-definite ordering, then G inverse is bigger than H inverse. And then, okay, this implies that if two Laplacians are close, then the effective resistances are close for all edges. It also implies this Rayleigh's monotonicity principle, which is, I guess, very old, which just says that if I look at G plus gamma, if I add edges to G, the resistances only go down. Okay. Okay. So, yes.
What's the precise statement here? H is sparse version of G, right? So some edges will disappear.
Oh, yeah. So the precise version of this is, so I'm looking at E as just a pair in H. Yeah. So I mean, the statement is actually for every pair of nodes, the resistance in G is approximately what it is in H. So I mean, I'm not actually concerned about what edges are in H, although I will only be applying this to edges in H. Yes. Okay. So now this is this so-called Resparsification algorithm, which they have discovered in this paper, which is the following. So the input now is H, which is a sample from the resistance distribution of G. And I'm going to keep track of which probabilities the edges in the sample, I'm going to keep track of which probabilities the edges in the sample H were picked with, okay, P sub E. And I have this gamma, these new edges that I'm getting that I have to figure out how to do something with them. The output is going to be H prime, which is a sample from G plus gamma, okay, with probabilities, with the next, sample, probabilities P prime. So the algorithm has two steps. So one is compute the new resistances. So I just added this gamma, right? So now for every edge in H and in gamma, compute the resistance of that edge in H plus gamma. Okay, I'm sorry, this is B transpose L inverse B sub B. Okay, but anyway, it can be done in nearly linear time using these Laplacian solvers, and call this thing P sub E prime. Okay, and then do this rejection sampling thing. So look at every edge that's already in the sparsifier, right? And now keep it with probability PE prime divided by PE. Okay, so the updated probability divided by the old probability. The updated probability is always lower, okay, because of this monotonicity property. If you keep it, then fine. If you reject it, then sample one of the new edges with the appropriate probability, the P prime over the total probability of the new edges. Okay. This is just actually what I told you about numbers in slightly more generality. Now the reason this works is, the first thing is that the resistances in H plus gamma are very close to resistances in G plus gamma, because H is a sparsifier of G. Okay? And the second thing is that this P prime over P is always at most 1. Okay? So the sampling probabilities are monotone decreasing. And now it's easy to check that if I actually have this, then the probability that a particular edge is included in the sparsifier is this P prime, which is the correct probability. Now, there are some approximations here, and you should be very careful about them, because the whole point of the previous thing was that it was not robust to these repeated approximations. And the reason this works is essentially because we're allowed much more slack in approximating the probabilities than we were in approximating the Laplacian in our objective function. So, I mean, the reason this works is because at every step we're comparing our graph to H that we have to some graph G that was there a long time ago that we don't even know about, right? We're able to keep this connection between H and G, which we don't have, right? And basically the reason is that even 100 approximate effective resistances are enough to compute a 1 plus epsilon quality sparsifier if you take enough samples. That's where the slack is. We have a lot of slack in the number of samples. I can take 1,000 times as many samples, and this is what allows me to sort of reset the error at every step. And then, because these solvers take m log n time, the amortized update time per edge is poly log n, although the worst case update time is bad. Okay, so that's the streaming algorithm. Here's a summary of what I showed you. So the first is this reduction to a linear algebra problem, which sort of revealed this interesting electrical information about a graph. The second is just how to solve this problem using random sampling, which was essentially known, and then how to compute the resistance quickly using Johnson-Lindner-Strauss. And the third is this streaming algorithm. And I want to end with open questions. So there are a lot of open questions here. So when I talk to people who actually applied this, who use this on actual data, they usually have the following concerns. So one is they would like some kind of locality. They would like some sampling probabilities that only depend on, they would like to calculate sampling probabilities for an edge, only depending on things that are somehow near that edge. I don't even know what the notion of nearness is, but several people have asked me about this. Nobody likes to solve linear equations to compute resistances also, even though there are theoretically linear time algorithms for doing it. Like, I met someone who was applying this to like graphs from the brain, and this was like a major problem, actually solving these linear equations. Can you do this without the log n and anything faster than n to the fourth right now? That I don't know. Can you do streaming spectral sparsifiers with deletions? So Andrew talked about how to do cut sparsifiers with deletions with n log n, which is amazing, which is like, I mean, it's a much harder thing to do. And currently the status of doing this for spectral is n to the 5/3. So clearly what I just showed you relies very strongly on the fact that you're only adding edges. So I don't know what happens if you try to delete edges. There are good parallel algorithms for solving linear equations that have depth m to the 1/3, but again, related to the first point of computing resistances, can you do better than that? And then can you do anything for directed graphs? So you can't sparsify directed graphs, that's known, but can you do anything for directed graphs, basically? And then can you do other things in the steering model, like Wells for expanding trees? Okay, that's it.
The error estimate, the 1 + epsilon, doesn't build up somehow.
Yeah, so it doesn't build up because so the invariant that you maintain is that you maintain samples that are within some constant of the correct distribution, okay? And you can make that constant kind of big, okay? And because you're able to actually get 1 + epsilon quality sparsifiers in every step, so it's crucial that you don't update, so these probabilities PE that I'm passing around, right? It's critical that they're the actual probabilities with respect to which the edge was sampled.
With respect to H?
With respect to which it was sampled in the whole process. So that's actually a subtle point, but that's what makes it work. Yeah. Yeah, okay. So.